This is the first lecture of Chapter 12 on organic chemistry. So we're switching gears a little bit. We're still talking chemistry, but you won't really need much on your periodic table for this chapter. This is more application of the chemistry that we talked about in previous chapters. So organic chemistry, what is organic chemistry? This is the study of compounds where carbon is the main element. So these are any compounds where carbon is going to be in that compound. So we're going to be talking a lot about what we call hydrocarbons. So those are compounds that obviously contain carbon, but also hydrogen. The compound for a organic compound does not need to be made by a living organism. There is a misconception that organic compounds are only made by plants and animals. There are a lot of organic compounds made by plants and animals, but they are not required to be made by a plant or an animal or any, a fungi or a bacteria in order to be organic. They just have to have carbon as the main element to be an organic compound. All other compounds that are studied are studied under inorganic chemistry. The thing is organic chemistry is a pretty large branch because a lot of compounds are actually based in carbon. So most of our known compounds today are organic, and we're going to take a look as to why. Some of these that obviously you're built out of organic compounds. We're going to look at some of those. This also includes things like gasoline, plastics, alcohol, foods, flavorings. We're going to see these as we go through this chapter. So why carbon? Why are we especially looking at carbon, and why does it make so many different compounds? Well, it goes back to the valence on carbon. So if you look at your periodic table or think back, what is the valence number of carbon? How many spaces does it have open? Sorry, my allergies are acting up. How many electron spaces does it have open to make bonds? It's 4. So it needs 4 electrons in order to get that stable state. And so if it's got a valence of 4, how many bonds can it make? A single carbon atom can make bonds with up to 4 other atoms. So it can make the compound like you see here. This is methane, so it can make a single carbon can make bonds with 4 hydrogen atoms, or it can double bond, as we saw in a previous chapter, with other carbons. And so because of these options, carbon is kind of like the ultimate Lego block, or the ultimate Tinker Toy, if you're familiar with Tinker Toys, the Tinker Toy piece, because it has these multiple bonds that it can make, and it makes almost unlimited combinations available to make these compounds. And so this is why we have so many organic compounds that are created that carbon is the base of. Now, even though the combinations are unlimited, they do fall into patterns that can be grouped, and that's what we're going to look at here in this first section of Chapter 12. So I mentioned hydrocarbons, so let me move my face out of the way. So hydrocarbons, these are organic compounds containing what 2 elements? Hydrogen and carbon. So the simplest hydrocarbon is methane, the one that we just saw on the previous page. So we've got the different formulas here. We've got the molecular formula, so it's written out with the elemental symbols. And then this is its structural formula. So how we saw in the previous chapters, how you write a bond diagram. So single bond between each carbon and hydrogen. So that is our methane. But with hydrocarbons, there are thousands of possible arrangements because each new carbon that you add adds more possible bonding arrangements. So we can have, for example, just with 2 carbons, there are 3 options to bond with that. So you can see those over here. So we can bond a single bond between those carbons and fill the rest of the bonds up with hydrogen. We can double bond with those carbons and then fill up with hydrogen so the number of hydrogens reduces. Or you can triple bond between those carbons and then the number of hydrogens reduces even more. Because remember, because carbon has those available 4 valence electrons openings, they can do single, double, or triple bonds between each other to share those electrons. So that gives us a large variety of options when bonding these together. So the octet rule does apply, so the number of hydrogens changes, like we saw over here, with 2 or 3 bonds. So if you count them up here with a single bond, you get the 6 hydrogens. So that counts for the 4. So you've got 1 bond for this carbon to the other carbon, and then 3 bonds on this side. So that fills the 4 missing electrons for the carbon on the right-hand side. And then 1 bond shared between the carbons. That's 1 for this carbon. 3 hydrogens on this side. That's the 4. When we do a double bond, we now have 2 on each carbon, so 2 here. That reduces the number of hydrogens because we only have 2 spaces left to fill. And so then if you go down here to our last one, same thing. We have 3 bonds now between the 2 carbons, and so we only need to fill 1 more space for that hydrogen. It reduces the number of hydrogens. So this is the first kind of grouping that we see as far as organics. So the first one we saw in that group is what we call the alkanes. The alkanes are hydrocarbons with a single covalent bond between the carbons. So just single bonds between the carbon-carbon in the molecule. Now these alkanes can be straight, like we just saw in the pictures for those diagrams. So they can be, oh, I can't grab my pen like that. Let me grab my pen. So we can get them where the carbons are sitting like this, all branched together, and then have the hydrogens coming off of the sides. Or you can get where the carbons are going to sit like this. So this would be a branched version of that same molecule. Or you can also get, oop, that's a really weird looking C. You can get carbon rings, which we'll see in some other structures later on, but it would look roughly like something like that. So the key here is you're looking for, if it's an alkane, it's a hydrocarbon that contains only single covalent bonds between those carbons. So these are the least chemically reactive of the hydrocarbons. So they're not going to do a whole lot if you try and react them. Now they will react, but not as much as the other ones, as we'll see. And each higher molecular weight alkane has an additional carbon H2. So what do I mean by that? So each of these groups of the hydrocarbons has a little formula that goes with it. So this is the standard formula for an alkane. So CN, N is for the subscript of the carbon number. And then that tells you that the H, the hydrogen, is going to be 2 times that N plus 2. So that's what we mean by this. Each time you go up a carbon in the alkanes, you're going to add 2 more hydrogens. So an example of an alkane is methane. And you'll start to notice as I talk about these guys why they're alkanes. They end with ane in their name. So we've got our first one, methane. So if we want to go up to the next higher molecular weight, the next one up would be C2. So Cn would be 2 here. So that would give us H would be 2 times 2 plus 2. So that would mean that the next alkane up would be C2. And so we've got 2 times 2 is 4. So it would be C2H6. Okay. Which is actually, if you go back to the slide before this, you'll actually see that on the slide before this, and that is ethane. So, and then after, there we go. After you get to C5H12, they do follow a pattern as far as their names. So you may notice that you've got methane and ethane. Those don't really seem to make a lot of sense. They're just a kind of traditional type naming convention. But after you get to C5, you're going to use the Greek prefixes. So, for example, C5 is pentane. C6 is hexane, and so on. So when you get to C8, it's got 8 carbons, that's going to be octane. Okay. So ane is the alkane. It's going to indicate the single bonds for this group. And once you get to C5, then the prefix will tell you how many carbons are in it. Before that, you just have to learn the names for those guys. So here are the alkanes. So as I mentioned, the first 4 have odd names. Here's C5 with pentane. But you've got methane, ethane, propane, butane. These probably mostly sound familiar. Most people know methane. You might not be familiar with ethane, but most of us know propane from cooking. And butane you may know from lighters. A lot of refillable lighters are filled with butane. And then above that you get pentane, penta for 5, hex for 6, hep for 7, octo for 8, nona is 9, and deca is 10. And you can see that they get bigger. Now here you're seeing them all in their straight chain forms, but like I mentioned, these guys can be branched or in ring forms, so they can be wrapped around into rings.